get things going here. So it's a pleasure to introduce Rachel Greenfeld from the Institute. Here at the Colloquium, Members Colloquium series for the term. So this is the last one for the term. And she will talk to us. I was looking then thinking, did Einstein know what P-adic numbers were? You'll answer that question, of course.
Yeah, it's not Einstein that you think about. So this is the answer. But...
okay. At the Institute, we think of a certain answer. Okay, Einstein, P-adic Sudoku, Dominoes, and Decidability.
Thank you very much, and it's a pleasure to be the last speaker for this term. So the talk that I'm going to give is based on a joint work with Terence Tao. And I do want to emphasize that all the results that I'm going to present here today were written here at the Institute. So this is also my opportunity to thank the Institute for the support and many aspects of support and the atmosphere that we have here that made my research possible. Okay, so let's start with the Einstein part of the title. This is a beautiful Escher painting of a tiling by translation and rotation of one lizard. I call it a monotiling because we use only one shape to tile the plane. And looking more carefully into the structure of this tiling, if I refer to if I refer to this grid that you see here behind, if I refer to it as the integer lattice, then we can see that this tiling is invariant under translation by even integers, by the lattice 2z2. So this tiling is periodic, or throughout this talk, when I say periodic, I mean invariant under translation by some lattice, where a lattice is a discrete subgroup of the space whose quotient is compact. So this tiling is periodic, and a famous problem in the area is the Einstein problem. And Einstein here is Einstein in German.
Okay, well, you corrected me there. He didn't know what P-adics were.
And this problem asks about the existence of an aperiodic monotile or an Einstein, a tile which does not admit any periodic tiling. The answer to this problem was found to be positive. For example, very recently this year, in March this year, the hat was discovered to be an Einstein by translations, rotations, and reflections. And this is not the first Einstein that was found, but this is a very simple one. This is the first polygonal one. So we see that we can find Einstein already in the plane and very, very simple ones. And to prove that this is an Einstein, the authors, what they do, they prove that there is some underlying substitution system that any tiling by the hat must obey. And so this first gives that the hat is a tile because we can tile arbitrarily large regions with it, but also the substitution system does not allow the existence of any periods, and so the hat is an Einstein. So we can be very greedy and say, okay, this is an Einstein, but we use translations, rotations, and reflection. And if I want to find an Einstein by translation and rotations only, the hat is no longer an Einstein because we need two tiles, the hat and its reflection. So I want to ask if there exists an Einstein by translation and rotation only. 2 months after the discovery of the hat, the same authors, they discovered that there is an Einstein by translation rotation only. These are the specters. And again, to prove that this is an Einstein, the the author revealed some underlying hierarchical structure that any tiling by the specters must obey. So we see that if we allow translations and rotations, then we can find very simple aperiodic monotiles already in the plane. So I want to ask, what about tilings by only translations? This is the subject of this talk, translational tilings. And since this is our subject, let me define translational tiling formally. So G is some additive abelian group from now on. And I look at some measurable set, let's say bounded set of positive measure in G, and I want to know if there exists a set A, a translation set such that if I translate my set F along A, almost every point in G is covered exactly once. If such a set A exists, then I say that F is a tile, translational tile, and A is a tiling by F. So this is the definition. And these are some examples that illustrate this notion in the plane. And I want to turn your attention to the fact that all these examples, the translation set, the tiling is along a lattice, a discrete co-compact subgroup. I also want to introduce this notation, so this orange notation for given a set, a bounded set of positive measure and a group G that contains F. I want to know, I denote, this orange notation denotes all the tilings of G by F. And given this object, this space of tilings, there are some natural questions that I can ask. First question is, suppose that we are given G and F, can we determine whether this space is non-empty? Or can we determine whether F tiles G by translations? Suppose that it's not empty, and I want to know how does it look like. And this is a very general question. A more particular question is, does it contain a periodic set? So suppose that the space is non-empty, must it contain a set that is periodic? In other words, we want to know if there exists a translational Einstein. So these are the questions that we will try to solve in this talk. And in order to start to build our intuition towards these questions, let's explore some examples. The first example is in ZD. So G is ZD, and F is just a singleton. In this case, F is a tile, because if I translate it along G itself, but along ZD, every point is covered exactly once. And in fact, it's very easy to see that this is the only tiling of ZD by a singleton. So we completely understand the space of tilings in this case, but this is too easy. See another example in the discrete setup. And now my G is a Z, and F is the set of the point 0 and 2. So I put one copy at 0, another copy at 1, 4, 5, 8, 9, and you can already see the pattern. This green set is going to solve this tiling equation. So we have that this F is again a tile of Z. And it's not hard to see also that the space of solutions or of tilings in this case consists of all the possible translations of this green solution that we found. So this, in this case, we have that the tiling is unique up to translation. So we have some kind of rigidity in the structure, There is another thing that I want to say about this example, which is, as opposed to the previous example where we had a lattice tiling, in this case, this green set is not a lattice. It's a union of two cosets of the lattice 4Z, but it is still periodic. So far, we have seen only sets that do tile, but of course, this is not always the case, and this is a non-example. So I want to tile Z by the set of the point 0, 1, and 3, and this is impossible because, for example, there is no way to cover the point 2 without overlap. So these are some examples in the discrete setup. Let's see some examples in Euclidean space. So now we are in the plane, and my F is a symmetric hexagon, and you can see that it tiles, and we have this honeycomb tiling, and in fact, this honeycomb has a very rigid structure, and in other words, this space of tiling consists of just one lattice and all its cosets, all its translates. So it's again unique up to translations. But this was not the case when I wanted to tile my backyard with a rectangle, because I had the freedom to shift the rows independently. This is actually my nephew's. It's not me, I just took the picture. So we had the freedom to shift the rows independently, and we can generalize this example and consider cube tilings in all dimensions. And cube tilings, they sound like naive example of tilings, but it turns out that their structure gets extremely complicated in high dimensions. So, one important takeaway from this example is that the higher the dimension, the worse the structure can get. And this is a very important lesson that we learn from this example. And it will become important later in the talk. So equipped with this intuition, hopefully we feel a bit more comfortable with the notions of translation tiling at this point. I want to go back to our question about the existence of aperiodic translational tiling. So the periodic tiling conjecture suggests that the answer to this question is no. Every translational tile must admit at least one tiling that is periodic, invariant under translations by some lattice. One reason why we might care about this conjecture is its connection to decidability, or the question whether there exists an algorithm that computes in finite time whether a given set tiles or not. And this is because Wang showed that if the periodic tiling conjecture is true, if every tile admits a periodic tiling, then we get the decidability of this tiling question. So there is a good reason to study this periodic tiling conjecture, and there are also many ways to study it. I will not be able to talk about all these different perspectives to the periodic tiling conjecture today, but all these techniques were applied to the study of the periodic tiling conjecture, and I still wanted to show you this slide just in order to say that there are many perspectives, there are many paths to this problem, and maybe if we understand all these different perspectives to the problem, we will be able to finally solve the question. Okay, so what do we know about this conjecture? Before I try to answer it, I want to show you some easy but non-trivial reduction. So the first reduction is that if we found a counterexample to the periodic tiling conjecture in ZD, we can inflate it in some rigid way to give us a counterexample to the periodic tiling conjecture in RD. So this is the first reduction. The second reduction is that if we found a counterexample to the periodic tiling conjecture in some quotient of ZD, we can pull it back in some rigid way to give us a counterexample to the periodic tiling conjecture in ZD. Okay, so far, are there any questions?
Sorry, what was the result Ligarius and someone else proved you some slides back before the slide?
The conjecture? Yeah, this is a conjecture.
Okay.
They did prove something.
Oh, I see. They formulated the conjecture.
Yeah, they formulated it in RD, and Stein was the first to formulate it in ZD, and Greenfeld and Shepard in their book about tilings, they didn't formulate it, but implicitly they suggested it. Okay. So is this conjecture true? What do we know? We know that in Z it is true. This is an easy result of Neumann. This is just a pigeonholing argument. We know that just by modifying this same argument, we get that it's true in virtually Z spaces and the space of the form Z cross finite abelian group. Ligarius and Wang, they did prove that the periodic tiling conjecture is true in R. And they used Puya analysis method to do that. Bouquet, Divat, and Kenyon, they proved that the periodic tiling conjecture is true for topological disks in the plane, of course. Venkov and McMullen independently, they proved the periodic tiling conjecture for convex domains in all dimensions. Szegedy proved that in ZD, for any D, the periodic tiling conjecture is true for tiles of prime cardinality. And very recently, Bhattacharya proved in a very interesting, I would say a breakthrough result of Bhattacharya that the periodic tiling conjecture is true in Z2. And it's interesting because he introduces a new approach, new ergodic theoretic approach to the problem. So we had that this was roughly when I arrived to UCLA and Terry and I started to work. And we thought, okay, we have this result in Z2. We reproved it using a much simpler argument. And we thought, now we have very good understanding of the two-dimensional case. Let's do the virtually Z2. Z2 cross finite abelian groups. But it turns out that the periodic tiling conjecture is no longer true in virtually Z2 spaces. So we constructed a counterexample to the periodic tiling conjecture in Z2 cross G node for some finite abelian group G node. Just a second. Now we have that periodic tiling conjecture fails in some quotient of ZD. So we can use the reduction that we saw to pull it back and give us a counterexample in ZD. And we can inflate this counterexample to give us a counterexample in RD. So there is a sufficiently large here in the statement. I want to say something about it. So first, it fits with our takeaway that the higher the dimension is, the worse the structure is. The sufficiently large can be made explicit. So our construction is explicit and we can compute it, but we didn't do it just because it's very, very, very far from what we believe to be optimal. And in particular,
sorry, maybe G0 is very big.
I will be able to say something about it after I discuss the proof.
And the set in RD, do you know something about it in your counterexample?
Yeah, so it will look like finite union of jigsaw puzzles. So rigid fundamental domains of RD mod C. But very, very complicated. Because it comes from ZD and we just inflate it. Okay, so it's very far from what we believe to be optimal, and in particular, we don't know if the periodic tiling conjecture fails in R2 or Z3. It's still open. I will say another thing about this sufficiently large. So D here in this statement is going to be very, very large, something like 2 to the 2 to the 20. But in fact, we don't use the full complexity of ZD. We really build our counterexample in a virtual Z2 space, which kind of suggests that the periodic tiling conjecture should fail quite early in terms of the dimension. Any question before we discuss the proof?
Can you remind me the theorem you have between comparing ZD and RD was only one direction? So
Right.
if you have a counterexample for ZD, you can construct one from RD, but not the other way around.
This is open. This is something that we try to study now. We know that they are equivalent in the one-dimensional case. Lagarius and Wang show that, and that's how they prove that the periodic tiling conjecture is true in R. Just reduced it to Z.
Are you going to return to the decidability?
Yeah, I will talk about this. But there is a connection between the proofs. So I'll start with constructing this counterexample. And the counterexample consists of introducing some Sudoku puzzles. So before I introduce our Sudoku puzzle, I'll remind you, if somebody forgot, what a usual Sudoku puzzle is. So we have a solution to a usual or regular Sudoku puzzle is a function on a 9 by 9 block square that such that whenever we restrict this solution to any row or any column or any such 3 by 3 block, we get a permutation. So this is a usual Sudoku puzzle. And our Sudoku puzzle, so the board for our Sudoku puzzle has infinite height and width that's equal to p squared, where p is a number that we fix in advance. It's going to be either sufficiently large prime or sufficiently large power of 2. In the pictures that you are going to see in the following slides, p is going to be equal to 4, but this does not meet the reality. In reality, we need p to be something like 2 to the 10. I just was not able to make such pictures, so we'll get our intuition from the 4 case. So this is our Sudoku board. And a solution to our Sudoku is a function on the board that takes values in what I call here the set sigma p. It's z mod p without 0. And why did I call it a Sudoku? Well, because we have some constraints on lines of the solution. Whenever I restrict the solution to any line of integer slope, I want it to obey some P-adic structure that I will describe in a few minutes. So for example, when I restrict the solution to this line, or this line, or this line, any line of integer slope, I want to see some P-adic structure. So this is why we call it a Sudoku. And then we show that under these constraints, all the solutions that we get are non-periodic. They don't have any vertical period. And so we have a puzzle that admits solutions, but none of the solutions is periodic. So we get an aperiodic puzzle. Okay, fine. So we have an aperiodic Sudoku puzzle. What does it have to do with tiling? So this is step 2 of the proof. In step 2, we develop some tiling language by which we encode the Sudoku as a tiling equation. And since the Sudoku is aperiodic, we get an aperiodic translational tiling. So let's start with step 1, constructing the Sudoku. And the Sudoku consists of, or the main ingredient, the key ingredient for the construction is this function f sub p. It's a function on the integers. What it does, it takes any integer and returns the last non-zero digit in the base p expansion of the number. And if such a digit does not exist at 0, we just set our function to equal to 1. So let's see what we get. Again, we're in the case p equals to 4. And this is a cutoff of the function f4. So what do we have here? If I restrict myself to just the white cells, they are periodic. So that's nice. But the problem is that there is this set for z, the numbers that are divisible by 4, that breaks down the periodicity. So we look into this set and try to find a period again, but there is this red coset, the set that of numbers that are divisible twice by 4, and they are they break down the periodicity again. And this happens in every scale of p. So in every scale of p, we will have one coset that breaks down the periodicity. So we end up with a function that is non-periodic, but is almost periodic in the sense that it is a limit in density of periodic function. This is the main ingredient, and having this fp, we define a class of sequences of length p squared, as a class of functions, all of which are rescaled versions of the original function fp. So let's see some example. This is one sequence in our class, and it's kind of similar to the behavior of fp in that the gray cells, they have the same density as the bad coset of fp. This is another example of a function in our class, and this in this example, the density of the gray cells is already 1/2, and it's not exactly the same as what we had before. And this is another example of a function in our class that doesn't have any gray cells at all. This is not at all looks like the original function fp. So we have many functions in our class, and using them, we define an SP Sudoku solution to be a function on our board, such that whenever we restrict it to any line of integer slope, we see an element of the class SP. So here's an example of a Sudoku solution. This is actually a standard SP Sudoku solution. It's standard because every column is just FP. In particular, this example is non-periodic because the columns, they are non-periodic. This is another example, which is non-standard, but still it is not periodic because every column is a shifted version of FP. But the problem is that this is also an SP Sudoku solution, and it is periodic. We want to find a puzzle that does not admit any periodic solution. So we want to exclude these two nice examples. And to do that, we will add another constraint on our puzzle. We call an SP Sudoku solution a good solution if, in addition to the previous constraint, it also obeys the constraint that every column is what we call an almost periodized, periodized permutation. So for any column, there exists a permutation such that this equation is satisfied whenever.
When you talk about almost periodic, on what group are we talking about? And what's the notion of? You said Vesikovich, but why that?
Yeah, so it's almost periodic in the sense that it's a limit. It's stronger than the regular almost periodicity.
Stronger than Bohr.
when I say almost periodic in this concept of Bezikovich almost periodic, I mean that it's a limit of periodic function in density.
Okay, I understand.
Okay, so what this constraint gives us is that we have the correct amount of gray cells in every column. So using these two constraints, we show that any good SP Sudoku solution must be non-periodic. And of course that it admits at least this standard solution. So we have a puzzle that admits solution, but none of them is periodic. So we get an aperiodic puzzle. I will not discuss the proof of this result, but maybe I'll just mention that the proof of this reveals some, again, hierarchical structure of Sudoku solutions. And this will be relevant later for the undecidability construction. So what I mean by hierarchical is that we play kind of Tetris. We first analyze the white cells, and we have the structure that we want, and we have the P-adic structure that we want, and then once we know that they have the structure that we want, we just remove them like we do in Tetris, and we show that we show that the remaining puzzle, the remaining function, the remaining function after removing this white cell is again a Sudoku solution. And therefore, we end up with, after iterating infinitely many times, we get the P-adic structure that we want. Okay, so we have an aperiodic puzzle. Now we need to encode it as a tiling equation. And to do that, we use some tiling encoding approach. And this approach allows us to encode first-order sentences as tiling equations. So for example, if I want, this is an example of tiling encoding. I want to say the sentence, this green sentence, the set A is a graph of some function from Z2 to a finite abelian group G0. Instead, I can say that A solves this tiling equation where we have a vertical tile and we tile this whole group. And the proof is easy. A solves this tiling equation if every slice of A solves this tiling equation, but this just means that this slice contains only one point, it's a singleton, and we just encoded a vertical line test, and therefore we have a graph of function. So this is one example. Now my G0 is some cyclic group, and I want to say that the set A is a graph of some function from Z to this G node that also satisfies this additional constraint. It's a periodized permutation. But instead, I can say that A solves this system of two tiling equations. The first equation, again, we have here a vertical tile. So it just encodes the fact that A is a graph of some function from Z to G node. And the second equation, we have a horizontal tile. And this equation encodes this fact that this equation is true for every x in Z. I have time, so maybe I'll show you. So suppose that n is equal to 3. And this is Z. And this is the Z mod n direction. This is my tile. This is Z cross G naught. So I have a function. I already know that my tile is a function. So I take this vertical line and I decide to put a point of A, say here. So this covers these guys. And then I cannot put anything here because I'm a function. So I go here and I have a choice. I can choose between these 2 points because this is already covered. So let's say I choose this one. And then this means that I cover these guys. And here I already don't have any choice. And now I no longer have a choice. And you can see that we have a periodized permutation. Oh, sorry. What did I do? This gives a periodized permutation, and that's exactly what's written here. So we see that we can encode certain first-order sentences as system of tiling equations, and the key is that every system of tiling equations can be encoded just a single tiling equation if we just add a cyclic group at the cost of 1 dimension. And the idea is to kind of sandwich the tiling equation that we are given using this additional dimension, and we get just 1 equation, bigger equation in a larger group. So using this, we can encode paragraphs of sentences, a collection of sentences as just a single tiling equation. And this allows us to encode our Sudoku. So I will denote Gn by Gn the nth column of the function, nth column of the solution. And I need to encode 2 sentences. The first is that these columns, they create an SP Sudoku solution, but this is not enough because we know that there are SP solutions that are periodic. So we also want each Gn to be an almost periodized permutation. With our language, we encode these 2 sentences as a system of tiling equation in a virtually Z2 space. And then we encode this system as just a single tiling equation if we just enlarge the group by a cyclic group. And we end up with a single equation that must be aperiodic because it encodes the behavior of a good SP Sudoku solution. Any questions? So this is a diagram of the proof. The blue part is what we call step 1, is the step in which we construct the Sudoku puzzle and we show that it is aperiodic. The yellow part is the part where we encode this Sudoku as the tiling equation. We show that it is expressible in our language. And if we combine the blue with the yellow, we get this green conclusion that gives us an aperiodic tiling system in a virtually Z2 space. We can encode it as a single tiling equation in, again, a virtually Z2 space by adding 1 cyclic group. And then we can pull it back to give us an aperiodic tiling in ZD and inflate it to give us an aperiodic tiling in RD. So we see that there are counterexamples to the periodic tiling conjecture, but maybe this example is super crazy, as I told Peter before. It's going to be something that's very messy, and maybe if the tile is nice enough, the periodic tiling conjecture is still true. So in particular, we can ask whether it's true for connected sets. We know that it's true for convex domains. What about connected sets? So it turns out that this is a result with Michalis Kolantzakis, that there are connected counterexamples to the periodic tiling conjecture in sufficiently high dimension. And I want to, again, remind you our first observation that the higher the dimension is, the worse the structure can get. And what we do is we are given, we kind of connectify a counterexample. We are given a counterexample that's not connected. And what we do, we just construct what we call a folded bridge between the connected components of the original type. And this folded bridge, it costs 2 dimensions. So from any counterexample in RD, we can construct a connected one in RD plus 2.
So I have a naive question. Your things were ignoring sets of measure 0, or
Sorry?
you're ignoring sets
Yes.
of measure 0?
Yeah.
So why can't you just join your pieces by?
Yeah, exactly. We should be careful when we say connected. So we want the interior to be connected or something like that. Yeah, you're right. Okay, so there are connected counterexamples to the periodic tiling conjecture, but what about decidability? We know that there are counterexamples. If there weren't, this would have been have implied the decidability of tilings, but there are counterexamples, and this does not imply undecidability. So tilings can still be decidable. So what about the decidability of tilings? This is a result with Terry, a recent result in which we show that translational monotilings are in fact undecidable. This is the exact sentence, the statement. One asterisk about this result is that instead of tiling the whole group as we did before, we tiled just a periodic subset of it. This made our encoding much easier. Okay, so this is the result, and in order to discuss this result, how do we upgrade an aperiodic construction to give us an undecidable construction? I will have to introduce to you the domino problem. So we are given a finite set of decorated squares. This is this W. And we're also given some horizontal constraints on W and vertical constraints. And our goal is to cover the first quadrant of the plane with translated copies of the elements in W while preserving both the horizontal and vertical constraints. So of course that not any set of squares and constraints will give me a tiling. And so it makes sense to ask about the decidability of this problem. So given a set of squares, decorated squares, and some horizontal and vertical matching constraints, I want to know if it admits a solution. Is there an algorithm that will decide it for me? And the answer is no. This is a famous result of Berger from the 60s. So Berger encoded any halting problem as a domino problem. And we know that the halting problem is undecidable. This is a result of Turing. And therefore, we get the undecidability of the domino problem. So what basically Berger does here, like encoding here, means that the Turing machine halts if there is no solution to the problem. If and only if, there is no solution to the problem. So we have the undecidability of this domino problem. And what we do, we encode any domino problem as a Sudoku puzzle, a decorated Sudoku puzzle. So I will not get into the...
So the undecidability of Sudoku puzzle, I assume, is well known. Just of, I mean, there are many results of that type, right? Or just Sudoku games.
Sudoku games, like infinite ones?
I mean, I've seen many papers of that nature.
Yeah, so here we need to use this hierarchical structure. So what we actually use is the decoration, right, and the connection between. So it's not an arbitrary
Sudoku.
Yeah, an arbitrary Sudoku. We really need infinitely many scales. And I don't know how to do it otherwise, to connect it to the domino problem. And maybe if there is other Sudoku that's not decidable, I'm not sure if I can.
No, I'm not saying it. I'm just saying that the undecidability of that genre of problem, I think, is well.
It starts from Berger, and all the results, they go back to this domino problem or the Cantor diagonal argument. Okay, so what do we do? I will not get into the technicalities, but I'll just show you the connection between the P1 cross P2 scales and the T that we see on the right-hand side. So P1 in this picture is 3, and P2 is 5. And we'll look at the scales. This is a standard solution, so we just care about M. And this is the scale. And when the scale, here we'll have T. So when the scale is 0, 0, these are the white cells of the Sudoku. This is the decoration. When the scale is 1, 0, these are the pink cells. We decorate them with this piece. When the scale is 2, 0, these are the red cells, and we decorate them with this element of W. When the scale is 0, 1, this is the blue cells, and we decorate them with this piece. And when the scale is 1, 1, which is just a combination of the pink and the blue, that is why it is purple. We cover it with this decoration, and you can see the correspondence with T on the right-hand side. So that's, very roughly speaking, the correspondence between the decorated P1 cross P2 P-adic Sudoku puzzle and a domino problem. So these are the technicalities. We get an encoding of any domino problem as an SR Sudoku puzzle. So the domino problem is solvable if and only if the Sudoku puzzle is solvable. And this gives the undecidability of the Sudoku puzzles. And then we encode any such Sudoku puzzle as we did earlier as a tiling equation. And this gives the undecidability of translational monotiling. So this is the picture of the proof. And having this undecidability, the existence of an undecidable translational monotiling problem implies by one's argument the existence of an aperiodic translational monotiling again. And having an aperiodic translational monotiling, we can connectify it using a folded bridge construction, and this kind of summarizes this talk. So I'll conclude with some open problems. One is the optimal D where the periodic tiling conjectures start to fail. This is open. The next problem is what you asked me before about the connection between the continuous and discrete periodic tiling conjecture. We know that they are equivalent in the one-dimensional case, but this is open in dimensions 2 and higher, and we have partial results in dimension 2 right now that we try to improve. We can also ask about strong aperiodicity. So what happens with our aperiodic tiling is that when we pull it back from Z2 cross G0 to ZD, we create many periods. And the strong aperiodic tiling is a tiling that does not have any periods. So this is still open. There exists a strongly aperiodic translational monotiling. We know that the periodic tiling conjecture fails for a connected set. It is true for convex domains. What about topological disks? We don't know. And it will also be interesting to try, which we try right now, to apply the methods that we have been developing to study the periodic tiling conjecture to other tiling-related questions, such as Nivat's conjecture in symbolic dynamics and the Koven-Meyerowitz conjecture, which tries to classify one-dimensional tiles using some number theory criteria. Thank you.
Thank you very much. Any questions? Comments? Yeah.
I
You've got to ask a question about Einstein.
I missed, you mentioned the result by Kenyon and two other people, and then I thought that you asked the same question at the end about.
That was dimension 2. I think.
Topological. Oh,
Yeah, in dimension 2, we have a result for topological disk.
okay.
This is the best known result in the plane. But in high dimension for balls, we don't know.
Can you say something about the hat? What is so interesting? The thing you went through at the beginning. So is that deep discovery? Can you go back and explain? Is it obvious once you find it?
It's not obvious. It's not obvious to find it.
Yeah, that I'm sure. But once you find it,
You need
it's one
to
of
be
these things.
very, like, you need to
Is it easy to verify what you're claiming there?
know. But what's nice about their proof, I just mentioned one of the proofs.
Oh, sorry, to take you back to the beginning.
But maybe I'll just explain. So there are two proofs, and one of them uses, as I explained, this hierarchical structure, which is usually the way that you prove a periodicity. But I have another proof of Mayer's, one of the authors that does not use this. So they found some continuum of, actually this is not the only aperiodic tile that they found. They found a whole continuum, and by comparing the edges of the behavior or the dimension of the dimensions of the edges of this continuum, you get that all the things that are in between, except for finitely many, they are aperiodic. And this is really, regardless of this result, this new proof is really exciting, I think.
And what happens if you allow other groups, less rotation, translation, reflection? I mean, you could allow some non-abelian stuff.
Yeah, so when you start with non-abelian stuff, you need to modify the problem. So it is studied in the aperiodic order literature and also ergodic theory, but then the question is about strong aperiodicity and not the aperiodicity that
Counterexample.
it's very easy to find counterexamples of this type in the non-abelian setup because the tilings have much less rigidity.
So you have this picture of not your lawn, and you said that it gets much more complicated in a higher dimension. So is that already happening in dimension 3, or is it then still?
Oh, no, so this is actually, so there is this conjecture of Keller from 1930, which suggests that any cube tiling in any dimension must contain two cubes that share a common facet, a d-1 dimensional face. When I should say share, I mean completely share. And this conjecture after 60 years was found to be false in dimensions, first in dimension 10 and higher, then in dimension 8 and higher, and then the 7-dimensional case was proven to be true using a computer. So it gets really, really, really messy in high dimension. This is just what I described now, just one instance of this complexity of the structure in high dimensions of cube tiling.
But dimension 3 is still easy.
Dimension 3 is still relatively easy. Yeah, you can describe cube tilings in dimension. I think that Keller himself proved up to dimension 6. He proved himself.
Thanks.
Further comments, questions? All right, well, let's thank Rachel.